like to start off by saying it is an honor to be here. So I do thank the host for giving us an opportunity to be here to talk about what we at Infleqtion are developing. And as the last speaker had mentioned, a very important strategic partnership that we've developed with L3 Harris, and who's represented today by Chris Dorny here from L3 Harris. We will talk about a collaborative effort we have to advance what we refer to as a quantum RF receiver technology. It's a Rydberg atom electrometer, has very broad applications in sensing and communications. And we'll talk a bit about what we're doing to bring that out of the lab, get it in the field, and ultimately transition it into operational use.
You can go to the next one. Yes, my name is Chris Dorny. I am the head of quantum technologies at L3 Harris. And if William could figure this thing out, as I'll talk through it. So if you look at the ecosystem that L3 Harris is focused on, there's many ground operations. We've got space operations. We've got naval operations and subsea operations. And so if you look at this, today this is hundreds of different sensors, hundreds of different communication systems, and all of them require very big, installations. And with our quantum initiatives, we focused on a combination of quantum sensing, quantum communications, and quantum computing or quantum processing. And so we use these quantum sensors in order to be able to collect information. And like I say, today, that's, hundreds of different, installations. With the quantum sensors that, especially the ones that we'll describe, we're able to take these hundreds of sensors and be able to incorporate all of those capabilities in a single, sensor type platform and be able to represent RF, signals across a very broad range. We use these sensors and we transmit it in a secure manner across these quantum networks, and then we bring it back to certain locations, and we're able to run quantum algorithms and quantum computing in order to be able to create what we call actionable information that our that end users can utilize to be able to improve the work that they're trying to do. And our vision has become the trusted disruptor for quantum enabled mission systems throughout the world. And so we've partnered with Infleqtion in order to be able to in these specific sensors for RF quantum enabled sensing for these type of applications. So I'll turn the time back over to William.
Thank you, Chris. I did figure it out.
Perfect.
So let me just, for those who don't know anything about Infleqtion, let me talk a little bit about who we are. So we are a quantum company that specializes in the use of atoms for everything. We use atoms as sources of time in our optical atomic clocks. We use cold atoms for inertial sensing and gravity gradiometry. And we use cold atoms also in tweezer lattices for neutral atom quantum compute. But in addition to that, we use room temperature atoms and a technique called Rydberg electrometry to create RF sensor systems. And I use that word very carefully here, systems. What you see in that diagram in the dash box, all of that functionality, the antennas, the antenna feed structure, all the analog processing in the receiver, from the filtering to the low noise amplification to the mixing functions, are now actually performed by a device that's about the size of a quarter, right? So there's no more antennas. There's no more traditional metallic hardware necessary to be able to tune anywhere in the electromagnetic spectrum. This device here can tune from hertz to terahertz in frequency. There's no need to change antennas. There's no need to change receivers. All that functionality is now performed by the atoms through atom-photon interactions and quantum mechanical interference effects within the atoms themselves. This happens to be a multi-channel version, and I like to show this one because it helps you understand sort of the multitude of ways in which a technology of this can be used. Each of those cells are filled with a dilute gas. It's usually rubidium or cesium. We optically excite them into what are called these Rydberg states, and we take advantage of a couple quantum mechanical interference effects to be able to detect RF signals. Each one of those is tunable across almost the entire spectrum. So we can tune all those channels to the same frequency, and that turns that into a phased array. So we then get geometric gain, which has great applications. I can also tune each of those channels to contiguous portions of spectrum that are offset by the channel bandwidth. And by doing that, I can open up the front-end bandwidth of the receiver system to cover a much broader range of spectrum. And I can also tune this in a hyperspectral way, where each one is tuned to non-contiguous portions of spectrum. So for example, that top channel cell could be tuned to IR, looking for heat signatures. The one below that could tune to millimeter band for 5G, 6G applications. The one below that could tune to the K bands for satellite comms. The one below that to L band for GNSS. The one below that to tactical frequencies of MF through UHF. And the one below could be tuned to HF and below for strategic applications. All of that can be done with one single device, right? So there's a one for many reduction or convergence that you see happening here. One multi-channel device here is capable of replacing multiple full receiver systems. And again, full receiver systems, that's the antennas, the feed structures, and all the analog processing in that hardware. So this has come a long way, and it's been in development. I would say most of the work's happened within the last 10 years. But the movement to the fields happened really in the last 2 to 3 years, where we began building portable versions of this technology. You can see over there in 2023, that was our first attempt to take a version of the system, basically taking the laser systems and the electronics and the power supplies and putting them into racks that are mobile, and then taking the 1 cubic centimeter cell you can see over here, that is the actual receiver system, which is fiber coupled. And we brought that out to the field. We brought it out per invitation by the U.S. Army to the NetMod X, which is the network modernization experiment, where they ran a series of tests in the field, transmitting signals both unmodulated, modulated at HF through UHF, and we did remarkably well picking up all the signals throughout the entire event. And then we did, for the first time ever, demonstrated the ability to integrate and interoperate with 2 existing systems. So we actually took the output of this system, we plugged it into an EW system, and we made it better. That's all we had to do. And then similarly, we had some tactical handheld radios, these PRC-148D tactical radios, and we configured it to run SINGARS, which is it's a hopping waveform. And by the same mechanism, simply plugging it into the front end of the receiver, we made it work, and we set up a SINGARS link. So that was our first excursion into the real world, and it worked out very well. And since then, we've taken more advanced versions of the system out to various sites to put it through the ringer of testing. Last year in March, we were out at Edwards Air Force Base at what's referred to as the Benfield Anechoic Facility, the BAF facility, where we were able to test the system across a broad range of frequencies. And for the first time ever, we were able to show that we can dynamically change the instantaneous bandwidth of this receiver system, and that's a big deal. We have the ability to change the rate at which the atoms can respond, and therefore the instantaneous bandwidth. We can change it in real time from narrow band to wide band, and we demonstrated that to the U.S. government. And then in August and September, we had the opportunity to be at APG, the Aberdeen Proving Grounds, where the Army put it through testing to see how well it would do in a contentious environment, or in a congested environment where there was lots of interference, and it performed remarkably well. And what you see over here on now on the right-hand side is where it is today. Now, we've been able to essentially shrink it down further without fundamentally changing the laser systems. We've been able to squeeze it into about 14U. It's a small half rack. It's about the size of a small refrigerator. It's fiber coupled out to a 1 cubic centimeter cell. And that cell there is a representation of what we've done to integrate it. That is, we've integrated the atomics, the micro-optics, and electromagnetic components into a cell that is 1 cubic centimeter. That's essentially the size of a sugar cube. So this is where we're going. So we're at a point of technical maturity where it is appropriate now to start thinking about how do we productize this, how do we further reduce it in size, how do we make it more rugged, how do we add in more features and functions, and again, continue to push the performance of the system. So today we're there in Gen 1. Within the next couple of years, we'll be in a Gen 2. We'll dramatically reduce the size of the back-end photonics and electronics that drive the system down to effectively 6U 19-inch rack boxes. And we'll take those 1 cubic centimeter cells and we'll tessellate them into a small array. And that's a 16-channel array. So that, as I said earlier, could be used as 16 independent channels, or collectively, you can use them to create an array for phased array operation. Tuning from basically 100 kilohertz easy out to tens of gigahertz. We do that today. We've done a lot better than that. And then longer term, the goal is to replace the diode lasers we've got with PIC-based lasers. That's how we are going to dramatically reduce size, weight, power, as well as drive the cost down and improve the volume manufacturing that's required to move this out into the real world. In that form factor, the back-end photonics is about the size of a smartphone today. It can effectively be handheld. That's something that can be placed on virtually any platform, large and small. So think of small sats, think of small UAVs, even handheld devices that would give you the ability to sense anything in the electromagnetic spectrum from hertz to terahertz. So with that, I'm going to hand it back to Chris, who's going to talk about additional ways that we are exploring right now to further increase instantaneous bandwidth so we can make this more appropriate for wideband applications that require much higher data rate performance.
Thanks, William. So when we went and started looking at our, our customer sets, our customers are always looking for, specific things within what they're trying to accomplish. So when we were talking to our customers, even though Infleqtion had this very robust product and well-performing product, our customers were looking for a combination of a little bit wider bandwidth, certain other applications for the applications they were requiring. So we had developed this spatiotemporal multiplexed receiver technology, which was essentially around overcoming the limited response time that each one of these cells had to go through. And so by utilizing and spatially separating portions of the signal and then multiplexing them together, we're able to get additional bandwidth, out of each one of these. And as you could kind of see in each one of the red, that's a portion of the signal that's getting spread out and then multiplexed, across it, so that we're able to get the additional, response time and performance, based on that. And then we're also using multiple or multi-beam system in this STM architecture in order to be able to increase, the bandwidth even more. And so from that standpoint, this example is, 9 beams, but you could do more or less depending on the application that the customer is looking for. So we're able to use a lot of the customization that Infleqtion has and the knobs that they have, and then utilize our STM architecture and multi-beam system in order to be able to provide a very flexible system that can be utilized to meet our customers' needs. Next slide. So then when you look at, the overall system, you could see that the Rydberg sensor is incorporated in pretty much all the areas that our mission networks are required. So they're in ground systems. They can be utilized in satellites, in airborne applications. And then once you collect all of that information, then it can be transmitted and brought back and use the compute technologies in order to create that actionable intelligence. And the combination of Infleqtion and L3 Harris is a very synergistic relationship where there's pieces that Infleqtion is doing on the excitation system and the subsystems, the vapor cells, the detectors, and then L3 Harris were on the multiplexing side, the software development, the testing, the overall system development. And so we're both taking these requirements and optimizing for what the customer needs. And our customers have noticed have been able to capitalize on these and been able to meet needs that they've never been able to accomplish before. Much better, sensitivity, much broader bandwidth, and we're just kind of in the early stages of this. It's been very exciting working with Infleqtion on this. So
I did want to add a couple things to this discussion here too. So first off, when you look at an architecture that, like Chris has shown here on the left hand side, that's how we historically thought about how to design and develop communication and sensing systems, right? And the platforms themselves become limiting factors. Platforms have size; they can only support so much power. They can, and they can, and volume. And if you look at low frequency operation as just one example, the physical size of some of those low frequency systems becomes prohibitive for use on small platforms. So the reason I bring this up is that as we move towards a quantum RF solution to some of these problems, it fundamentally not only acts as a replacement for some of those existing receiver systems, but it also challenges your notion of architecture. You're no longer bound by what classical systems allowed you to do in the past, and so it's actually forcing us, or not forcing, but giving us an opportunity to think of quantum as another set of tools that we can use for not only designing a sensor better, but designing networks better, right? The idea of proliferating these kinds of sensors across all platforms, giving all platforms the ability to access spectrum across the full spectrum, right? Not just in particular bands. That is game changing. And I would expect in the next 10, 15, 20 years that the architectures are going to reflect the use of these quantum technologies, which would be dramatically different. The last thing I want to mention here, as we have just a couple of minutes left to go, is this idea of a strategic partnership, right? We have a strategic partnership, and both our companies have presence in the United States, in the UK, and as well as in Australia, and we are working together to utilize that talent that we've got across all three continents, if you will, to go after and pursue AUKUS-related opportunities, and that has started, and so far has been it's been interesting, I'll say, and it holds a lot of potential.